Thank you very much. I'm really excited to be here today because PITMS is a partnership between the US and ESA. And so I'm really excited to share our first light results with you at this particular venue. And many of you are in the audience, including Tris. So thank you to our whole team for helping us do this. We were the first CLPS delivery. We were on the astrobotic mission. We did not make it to the moon. I think you know that, but it's exciting that we still got results from our mass spectrometer that are probably publishable. We'll see when we submit it. Oh, click back. Click back. I have a lot to tell you about, so I'm going to blow through these pretty quickly, but we've got stickers and swag up here, and you can talk to me until my face turns blue. I'm happy to talk about this more. So PITMS, like I said, is a partnership between NASA Goddard, where I am, and the Open University, funded by NASA headquarters in ESA through the NASA Provided Payloads Program for CLPS. So we were proposed way back in 2019. We flew earlier this year. The science for PITMS, it's an ion trap mass spectrometer. We're really interested in how the volatile species move around on the moon. And you heard this from many speakers already about other missions that also want to do this. So this is really great science, as you all know and love. We were supposed to be just a passive instrument on the surface of the moon, much like the LACE mass spectrometer during the Apollo missions, just passively sensing what's in the lunar exosphere and what the flux is over the course of a lunar day. So ESA provided the sensor, the mass spectrometer itself, and we provided the wrapper. So here's the sensor itself, a prototype of the sensor. It gets wrapped up into this box that becomes the mass spectrometer here, the EMS, exospheric mass spectrometer. We put it into this wrapper that Goddard built. Here it is being integrated onto the spacecraft. For reference, this is the IRIS rover. So sometimes when you see the Peregrine spacecraft, you'll see the IRIS rover with these little eyes that are the wheels, and we're right above it. So when you see the Peregrine spacecraft, that's where we are. We're mounted on a deck. We have a clear zenith looking view. So if we had landed successfully, we would have popped open our desk cover, had a clear view to zenith, and passively collected species as they bounced around the lunar exosphere. So yeah, it was a great launch. Oh my gosh, it was a really nice launch. I'm probably never going to see a launch as good again. These are amazing pictures that I didn't take, but they're from social media. We launched on the first flight of the Vulcan Centaur that has methane engines and solid rockets that turn white, and the methane turns blue, and you get these really pretty trails. This is the spacecraft being released. Everything looked nominal when it was released from the rocket, but then here's the trajectory that it took. It got all the way out to lunar orbit. This is the distance of lunar orbit. But yeah, the anomaly, as Brent called it, they had an oxidizer explosion, basically. So they tried to pressurize the oxidizer tanks with helium. The helium valve didn't shut off, and so it overpressurized the oxidizer tanks and blew a hole in the oxidizer tank, which vented all the oxidizer to space, which means you couldn't mix it with the fuel to get any thrust anymore. So not only did we not have thrust in the engines, we also had a big sideways thrust from the leaking oxidizer. So they recovered control of the spacecraft by using the pressurized fuel as a cold gas in the attitude control thrusters, and were able to regain control of the spacecraft. But then it just came around on a free return trajectory and intersected the Earth, and we burned up over the Pacific Ocean about 8 days after launch. But nonetheless, we got to turn all the instruments on, including PITMS. PITMS got 4 sessions. We got about 8.5 total hours of operational time. We turned on, which sounds kind of cheesy, but it's a big deal when you get to turn on successfully. So that was really awesome. We applied a software patch that we really needed to do to function. So that was really helpful to know that our flight software was working correctly. We did a functional test with our filaments and detector off so that we didn't break anything. We just knew that everything was operating. We turned the filament and detectors on and acquired actual data. We have a dust cover, like I said, on our aperture. So we had data with our dust cover closed. We popped that dust cover. We took data with the dust cover open. And then we downlinked a whole bunch of latent data. So we really put this instrument through a lot of its spaces, not everything that we wanted to do on the moon. And these were just really, really off nominal conditions. So as we talk about the data, it's the data that we have, the data that we got, and we're going to make the most of it. But this is really, really, really off nominal cases. This is not how we were meant to operate. We're well outside of our design parameters. There were lots of other things that happened very off nominally on this mission. So just keep that in mind as you're watching it. One of the off nominal things that happened is we were supposed to do operations at Goddard Space Flight Center, but instead I was in Florida in my hotel room. Everyone else was in their home offices. It was actually a really great challenge for us. We set up our operations to be fully remote on a virtual desktop before our international partners to be able to access NASA data. That was like a huge deal. But it ended up working out really well when we had the anomaly and we all were able to control it from our own homes. Okay, so here's our spectra just to show you kind of the performance of the instrument, which was amazing. These are two representative spectra. The blue is with the dust cover closed, the orange is with the dust cover open, and the orange is offset just to be able to show you what they look like. Our noise limit down here, 5 times 10 to the minus 11 millibars. I think in Tor, this is a millibars, they're approximately the same. That's about 1 count. We can't really detect 1 count. It's probably 50, 100 counts, something like that. So that gives you a feel for the noise floor. But you can see these nice, strong, well-formed peaks all the way out. We have about 14 mass to charge ratio 14 to about 130. And we got 80 spectra. So we were able to look at a whole bunch of species before and after the dust cover opened. Since LPSC, if you saw this at LPSC, we've applied a really rigorous calibration process where we adjust both of these axes to be correct as we can get them. We get this quantitative calibration to partial pressure. There's things in here to be aware of. There are artifacts and ghost peaks, but we've identified those. And also they were possibly count limited. We're ion counting, but when the door was closed, the dust cover was closed, these kinds of peaks are really, really high. It's a lot of pressure and it saturates the detector basically. So just be aware that some of the things we'll show you are lower limits and not as quantitative as we'd like. So this is sort of just the methodology for how we're looking at what PITMS detected. So the spectrum that I'm showing on top here as the blue spectrum is all of our data with the dust cover closed added together. So there's a little bit of peak broadening, but it's just to show you kind of what species we can detect. If you add all the spectra together, you should beat down the noise and really pull out the signal. And then we're modeling all the species that might be there. So here's a whole list of individual species in the model. There's combinations like terrestrial atmosphere, oxidizer, combustion products. The reason you have to do it is not just, you can say, you know, what mass this is, what mass to charge ratio is, but to say what species it is, you have to couple all of the individual lines from individual species, right? So just to show you, here's like a spectrum from nitrogen dioxide, the fragmentation pattern that you'd expect from electron impact. So as we do electron impact to do our ionization, you can also break up bigger molecules into smaller molecules, and they show up in any spectrum that you take as well. So you're really looking for the coupling, the fingerprint of each molecule, and then trying to deconvolve those from your spectrum to get sort of a least squares fit. Just to see what's there, not to tell you where it came from, just that's in our spectra. So in our spectra with the door, the dust cover closed, again, here's the model in white, and here's the spectrum in blue, and here are the species that contribute to this spectrum. So the major species that we have are water in terms of H2O and OH, but also H3O, and I'll talk about that in a minute. Oxidizer is here in yellow. So the oxidizer is MON25. It's 25% nitrogen oxide in nitrogen dinitrogen tetroxide. So that's the oxidizer, and we see giant whopping fingerprint of that. No surprise, that was leaking out. There's maybe some combustion products and maybe some uncombusted fuel. And with our dust cover open, I've scaled these to be similar to each other. The actual peaks are much lower in intensity, but I've scaled them so that you can see the components. The components are largely the same. I wonder if I can flip back and forth. The components are largely the same. The thing that's varying the most is the H2O to H3O ratio. Otherwise, it's pretty much very similar to each other. So even though the absolute intensity is lower, the species that we're detecting are there in very similar abundances. So interpreting these, in the circles is the water abundance. Now I've got it calibrated to partial pressure, and here's the oxidizer. And here's where our dust cover opened. So we have spectra just before and just after the dust cover opened. That's where you get that pressure difference. So for water, it's very, very high in the beginning. So that's expected. As we turn on, we are carrying water with us. We have water on our paint. So we're expecting to see a lot of that water come out. It stays very high and then it comes down. So that's about 3 times 10 to the -6 millibar. That's just a lot of water. Another way to look at that is that H2O, H3O ratio that comes from protonation of the water in the ion trap itself. And the higher water pressure you have, the more you're going to have those intermolecular reactions and drive it towards H3O. So this is another way of looking at it with our dust cover closed and our dust cover opened. Again, 10 to the -5 millibars of water. That's just a huge, huge pressure. For the oxidizer, you can see the same kind of behavior. It's high when we have the dust cover closed. It's lower when we have it open. That means that oxidizer got pushed in through our dust cover. It's not sealed. It's a labyrinth to keep out dust. It's intended to equilibrate. So that gas got pushed in while it was leaking around the spacecraft. And that's pretty high pressure. So we're modeling that as well. This is simulations using a low pressure gas model. This is what outgassing all around the spacecraft would look like of just water. It's kind of isotropic around the whole spacecraft. But the oxidizer doesn't get all the way over to PITMS. The oxidizer was leaking from the opposite deck. And if you model that, it's very hard to get enough pressure over to PITMS. So there's two things here. Maybe it's because the spacecraft was rotating and now we have the spice kernels to look at that. But maybe it's also because that oxidizer didn't just blow all the way out. It can leak through the spacecraft itself, especially through the MLI blankets. That provides a nice quick path right over to PITMS. So yeah, just to wrap up, we operated for 8.5 hours. We measured the spacecraft environment rather than the lunar environment. Lots and lots of water, oxidizer, fuel, combustion, maybe. All our data are delivered to the PDS. We just did that a couple weeks ago. It's going to be mirrored in the PSA, so all the data are there will be there for your viewing pleasure. And we submitted a couple papers already, more on the way. We also have a ground reference model that we're using to understand more about these kinds of species that we looked at and modeling that spacecraft environment. Like I said, this was a wild ride. We have a lot of lessons learned for CLPS providers, for CLPS instrument people. If you've got an instrument in this program and you want to talk to us, please do. I am free the rest of the year and I have travel money. So if you want to invite me to give a seminar, I would love that. So thank you for everyone who really helped us do this mission, and we're grateful for everyone. Thanks. Thanks, Barbara. We've got questions. I'm amazed that there aren't. Right.
Thanks, Barb. Roman Tartes, University of Manchester. Do you have an idea how long it would take if you sit at the surface of the moon for the the water background to sort of drop to background level?
No, we don't. I really wish that we did. We just didn't have enough time on the spacecraft itself. We know there was a lot of outgassing. The spacecraft was not clean. We could have made our instrument cleaner. We have the capability to do bake out, but we just couldn't do it on the time scale here. So we could have made our instrument much cleaner to really nail down what the spacecraft was outgassing and then measure that over time. That was one of our goals, but we just didn't have enough time series to do that.
Eileen Yanks, PSI. What is the most important lesson learned that you can share with a large audience for the CLPS paradigm?
Be flexible. Things change constantly, and you just have to roll with it. But learning by doing is a great thing to do. So don't be scared of it. Just be flexible.